Welcome back, Quadrature fans. My name is Marion Elena, and we're continuing our series on quadrature. And just been reviewing some of the videos that I've done before, and I noticed the plethora of errors, and just aware of it. It's kind of a grief. But those things happen. I have an idea in my head, and I draw things on the fly, and sometimes you pay for that, you know. It's that's the way it is. But let's see. Where did we leave last time? Yes, we had our Professor Theoremus Antiquitus was kind of in a pickle, and essentially he was criticized for being imprecise, you know, the estimates. So we really need to get better figures. We need the exact figures for these ratiometric iso invariants. K2, the area ratio, and C2, the tangent slope ratio. And those things, that's what we intend to do, is firm that up, make it exact. So, well, maybe a little bit of review so far of what we did, and then we'll firm up these ratios. So let's look at our old case, y equals x squared, like this. Y equals x squared, and we put our grid down. That helps us to draw things. Characteristic diagonal, and the curve itself. Ooh, nice. Okay. And so it would be the area underneath here. That's what we're looking at. And we're also looking at the tangent slope. And so, well, let's look at just a review. We've done this before, but I want to review it again. Let's zero in on this little one. 0 to a, 2a. This will be 0a squared, 4a squared, because it's x squared, 2a, you plug in, you get 4a squared. Alright, here's our little characteristic diagonal, and here's our tangent slope. And here's also the area of interest. This little wedge, and we compare that to the area of the box. So in quadrature, everything happens inside of the box, and the key is to think inside the box, because outside the box there's nothing to think about. Okay, that's kind of a warning. Alright, so let's just pull this point using rubber band geometry, and we're going to pull it. A, 2a, and of course 0a, 2a. It will look like this. And essentially, we pulled from here to here. We doubled our box. And we have doubled this area, going from here to here. If you put a fine grid over here, you see that everything scales proportionately. So the area inside here will just stretch. And also the slope. We see that here's a slope, and compare that to the diagonal. Well, here's a slope, here's a diagonal. The slope is more shallow. As a matter of fact, the rise is the same, but twice the run. Therefore, the slope has to be 1/2 of this slope. But the same thing goes for the diagonal too. That one's also shallow by exactly the same amount, 1/2. So the ratio of this slope to this diagonal is the same as this slope to this diagonal. And the ratio of this area to this box, same as this area to this box. These ratios are basically K2, the area ratio, and C2, the tangent slope ratio. And there's only one value for y equals x squared. There's a unique number. That's why it's iso ratiometric invariant. It's the same number. All right. Let's now do another pull in the y direction. Essentially, we're going to pull 4 times up. All right? Because here we're a squared, 4a squared. We're going to pull 4 times. And so what we will get when we do that well, we will get back to our, how the hell is this? I've got to make sure I draw it right this time. It's got to go here. There, I think I drew it better now. Last time I drew it incorrectly. It's the same thing. And again, going from here to here, this ratio of the tangent to this diagonal is the same as this tangent to this diagonal is the same as this tangent to this diagonal. It's C2. It's one number, C2. That's it for x squared. And it turns out that, well, we found it was approximately 2. And we will prove that it's exactly 2. Also, the ratio of this area to this area, this area to the box, same as this area to this box. Well, pull it now higher, essentially end up with this shape. So when we go over here, we see that the ratio of this area of this big wedge to the big box, they're all K2. It's the same. It's one invariant. That's pretty simple. So, really want to nail that. Nail it good. Okay. Welcome back. So, I have to collect my thoughts. And we're proceeding. But before we proceed, well, we need to give credit to whom credit is due. And a lot of these ideas are coming from Professor Norbert Weilberger around 2000 AD, roughly. In particular, he had an article, I think was it the Mathematic Monthly, and it's essentially, what's the name of the article? A new proof of Cavalieri's formula, something to that effect. And he's also got some videos called Famous Math Problem 10A and B. Worthwhile. I highly recommend that. So, give credit to where credit is due. Okay. The 5 attributes of areas, according to Weilberger: additivity, linearity, translation, dilation, normalization. Five amigos, they're your friends. Additivity, let's just briefly summarize them. I'm not going to prove them. That's beyond my capability. But, we kind of have a rough notion. Areas add. You can add chunks of areas, x direction, y directions. They all add, right? We have a gut feel for that. Okay. That's additivity. Linearity, well, if I say y equals 2x squared, things are going to double. Everything's going to double. It's all linear. It's going to be twice. If I say y equals 1/2 x squared, well, I end up 1/2, right? That's linearity. That's pretty simple. Do you understand? I understand that. Translation. This is a big one. This one really. This is key. What is translation? Well, let's look at it. It's like a frame of reference. It's used a lot in physics. So let's put that down. Here's our x frame of reference. And x begins over here. Here's 0. Here's A. A is some letter. Pick a letter.
B.
No, sorry, not letter. Pick a number.
50.
50 it is, and stick with it, okay? So what's 2A? That'll be 100. Okay. Okay. So that's what it is. Well, in translation, this thing's miserable. Just when you need it. Imagine this, that here's our x-axis, and superimposed on top is this t-axis, but t, it begins, 0 is over here. This is therefore minus a, and this is plus a, right? So you pick 50, so this would be minus 50, this would be plus 50. In terms of t, I show it as down here, but they're really superimposed right on top of each other. But that makes it cluttered. So essentially what we're saying that x equals a plus t. So if you plug in t equals 0, you're going to get x is equal to a. If you plug in t equals a, well, a plus a is 2a. You plug in t equals minus a plus a gives you 0. So you see how that works. So that's translation. And it is an invariant because the curve doesn't change, it's just a reference point. So that's translation. And the defining equation for translation is this: x equals a plus t. And then we just prove it. Very simple. That's translation. That's an invariant because it doesn't change the nature of the curve. It's still there. It's just, what's your 0 reference? That's all. Dilation. Well, that's my rubber band geometry. You take this thing and you pull it. That's dilation. And there are scaling. For example, you pull this point to here, you double the area. Now pull it 4 times. Well, that's 8 times the area. So you pull this point all the way to here, you have 8 times the area. That's dilation. And of course, normalization, well, that's our normalized k-factor that's already kind of built into these k-factors. They're normalized. It's a ratio. They're ratiometric. So, 5 amigos, they're really good. So, okay. Keep this in mind. And we're going to do something with it now. And let's look at our area. And again, we're looking at areas and slopes, or area ratios and slope ratios. And we're kind of treating them almost simultaneously together, which is a different, they're a really unique approach. That's my approach, because they're very much related, the slopes and the areas. They're very much related. Okay, so given this translation equation and y equals x squared, well, this would be area. All right. So we said that y equals x squared. But here x is equal to a plus t. So really, y equals a plus t squared. Pretty interesting. Let's crank that through. What is that? Y equals a squared plus 2at plus t squared. This is called a binomial expansion. The power is 2, and this is what you get. With binomial expansion, it's nicely summarized here using Pascal's triangle. 1, 2, 1. Do you see how this works? You see these are like, this is Pascal's triangle. That goes with this binomial expansion because we get 1a squared, 2at, and then back to 1t squared. You see that? And this will really become useful when we're doing higher powers. Then you will really see y to the third, to the fourth, etc. But we're already laying the foundation with, this is what we're going to be doing for the higher power curves. We're going to be using this Pascal's triangle. Anyway, so these ratios. Let's kind of look at what we have here, because what do we have? Well, we have a we have this one. So we have t. Now let's look at t from 0 to a. We're going to be looking at really this kind of a wedge. If you plug in a into here, see this a? Plug that, t equals a. What you get is a squared, right? That's the height over here. What about this one, the linear term? That's 2at. Well, that's going to be this. That's a linear term, right? What is this one? 2a times a. That's again 2a squared. You see it? 2a, plug in t equals a, and you get 2a squared. And then what about this one? That's just a constant term, right? A squared. So you get 1a squared, 2a squared, 1a squared. Yeah, you've seen this in our famous Pascal 1, 2, 1. 1, 2, 1. And so what happens if I slam these things together? Okay? What happens is you get a shape that's going to look like this. Alright? Watch this. A squared, 2a squared, a squared. Look at these. And look at them carefully. Here's a squared. That's our linear term, right? I mean, excuse me, that's our constant term. Right here. Alright? We're going from 0 to a. And we're working on the t-axis. So that's just a rectangle. That's this one here. Now add our triangle, 2a. It's 2a. This thing's a. And now add, and we're using additivity, okay? That's one of the attributes of areas. You can add that. And using Cavalieri's principle, namely, if you slice this up into tiny little sections, all right, like a really fine, and rearrange it, you can then stack it on top, and that becomes right here, all these little wedges. You see this? That just comes right across to here. That's Cavalieri's principle. You've seen it with a deck of cards, okay? So here we have a deck of cards. And it has some kind of an area. It has even volume, right? But let's just focus on the area itself. And now I shift it like this. All right? Has the area changed? No. That's Cavalieri's principle. And it doesn't have to be a nice, pretty, you know, this is kind of weird. It could be anything wild and crazy. I mean, look at this. Has the area changed? It's still Cavalieri's principle. So that's part of our additivity. And that's what we're using. So these three, and then look at it. That's that one. That's that one. That's that one. You see them? Constant. The linear term is a triangle. And then the quadratic, there's that one. And when you squish them all together, well, you get this kind of a shape. Okay. Notice one thing. Notice this shape here, this t squared, where we're going 0 to a on the t-axis. Okay? Here's our t-axis, 0 to a, right? 0 to a. Notice that it's the same thing as this x going from 0 to a on the x-axis. It's the identical shape. It's just it doesn't matter. Here we call it x squared, here we call it t squared. T squared over the interval 0 to a on the t-axis is the same as x squared on the interval 0 to a on the x-axis. It's identical. And that's key. Once we kind of know that, okay, let's put it together. Follow so far? All right. So the area. So what do we have as the area over here? What's the area of this thing? Well, it's going to be K2. That's our iso ratiometric invariant. K2 times the box 2a times 4a squared, base times height. 2a times 4a squared. That equals, what we're talking about is this area right here. Alright, that's the big wedge, this one here. This one is equal to, well, it equals this little one, right? You see it? What is that? Again, our K2. That's invariant. Doesn't change. Times, what's the base? A. What's the height? A squared. All right. Plus this, our constant term, we're talking here, a squared. Well, it's really 1 times base, which is this one here, see? A times a squared. See it? Plus, now we have a triangle. 1/2. The k factor for that is 1/2, right? Oh, you knew it. Times base a times, what's the height? 2a squared, right? That's the height of this triangle. Base is a, height is 2a squared. 2a squared. All right? Plus this one, the last one. What is that? Well, that's our second order, so plus K2, we're back to K2 times base, which is our A, times height. And it doesn't matter that you shifted it using Cavalieri's principle, it's still base times height. This and this is the same thing by Cavalieri's principle. Right? That's what we have. So K2 times A squared. Same thing as this one. This little wedge and this wedge here, they are one and the same, especially if you downshift it using Cavalieri's principle. Okay? And that comes from here. So essentially, what have we got? We got A squared, A squared, A squared, A squared, A squared. That A squared, that's just going to fly out of there. That cancels out. So that's out, right? You don't have to worry about that. So what do we have left? Well, let's reconfigure. So we got 8 K2 equals K2 plus 1 plus 1 plus K2. We have one equation, one unknown. We can solve this for you. Basically, 8K2, so you subtract 2K, that becomes what? 6K2? 6K2 equals 2. K2 equals 1/3. That's exact. K2 is equal to 1/3. Equals 1/3. That's a big finding. Of course, Cavalieri, I mentioned it, Bonaventura Cavalieri, he figured that out in 1640s. He already knew that. So that was known. But we did it using an algebraic manipulation here. Simply the translation, all of these really, they're all playing a role. Additivity, linearity, translation, dilation, normalization. They're kind of technical terms, mathematic terms. I call dilation my rubber band geometry. Anyways, that was a piece of cake, you know. But before we sign off on this one, let's just look at this one more time, and let's look at the relative areas. You know, how is this area compared to this area? The proportions. You have 4 areas. Okay? Let's look at, this would be the smallest area, so let's normalize by smallest area. So divide everything by K2, which you know is 1/3, right? Go to this equation. If you divide 8K2 by K2, you get 8 equals, K2 divided by K2 is 1, right? So plus 1 divided by K2, that's 3, right? 1 divided by 1/3 is 3. Plus 3 plus 1. 1 to 3 to 3 to 1. 1 to 3 to 3 to 1. 1, 3, 3, 1. Look at that. Back to our Pascal's triangle. This is amazing. Your function is 1, 2, 1. The areas are 1, 3, 3, 1. That relative weight. 1, 3, 3, 1. This is really, I think it's beautiful. But, okay. So that's area, but that's only half the story. The other half of the story, of course, is the slope. And don't forget the slope. You know, what's happening with the slope? Because we said we're going to look at the area and look at the slope. So let's continue on. I'm going to have to do slope. Slope at t equals a. That would be the tangent over here. See this? What is the slope of this thing here? That's the big question. And we estimated that it was 2 last time, using crude estimates. Now we're going to prove that it is 2. So, in a similar way, what is the slope? Well, okay. We know that well, the slope here is really C2 times rise over run. That's the characteristic diagonal. See it? Times 4a squared divided by 2a. Rise over run. That's this slope here. So we're comparing it to C2 times this gives you this. That's the whole idea, having this invariant. That equals. All right, let's look at each individual function. We want to know what the slope is contributed by each of these. You see it? How much slope does a squared give you? See this? How much? What's the slope of this function here? 0. Plus. What about this linear term? Well, that's really 2a. I mean, that is right off the bat, you know it's 2a. But think of it as rise over run. So it's 2a squared divided by the run, which is a, right? So that gives you 2a. Plus, what about the slope over here? See this third one? You got 3 functions. 1, 2, 3. 1, 2, 3. What's the slope over here? Well, it's, again, C2 times rise over run. A squared divided by a. That's it. Okay. And so let's look at that. You got a squared over a squared over a squared over a. That just falls out of there. Cancels out. It's gone. Let's collect it. So we're just going to have 2C2 equals, basically 2C2 equals 2 plus C2. That comes from this equation. That's one equation, one unknown. Solve for C2, you get C2 equals 2 exactly, which we kind of estimated before. But now we nailed it. So, and before we leave, let's just normalize everything by dividing by C2. So what's this? 2 divided by C2 is 2 equals 1 plus 1. And guess what? You know, that's this and this. See that? We're going to see that pattern repeat when we go y equals x third and everything else. Anyway, so good. Thanks for tuning. I'm Mary and Elena. See ya!